Well, first I'd like to thank Greg and the meeting organizers for a terrific meeting and a outing yesterday that I won't forget, but I do regret. So, in any case, so I was asked to talk about, like many of you, a topic that once I looked back at my email surprised me, but it is, I'll talk about that and a few other things. So this has to, the nominal topic was mass loss from planetary nebulae and AGB stars in ellipticals, and one of the motivations was that we just generally assume that the mass loss from the stars is thermalized to the velocity dispersion of the stars, which is the characteristic temperature of the system, and but it might be a little more complicated. I hoped it would be, because I wanted it to solve a particular problem. And the problem is that the mass loss from AGB stars is enriched, and the mass from supernova 1A is enriched, and you add them together and the metallicity should be about 3 to 5 times solar. Just for historical interest, this was a prediction before ROSAT went up, and so we thought this is going to be an easy confirmation with ROSAT. Didn't happen, still isn't the case. When you look at X-ray gas in elliptical galaxies or early type galaxies, it's somewhere between 1/10 and twice solar. Let's say it's typically solar. And so it's a conflict here. Maybe a lot of the metals don't get mixed in. We got the supernova 1As wrong, but then you need the heat from the supernova 1As, and I'll show you about that. So we did some work on this that eventually got published in 2 papers. I say that in an earlier paper we looked for the infrared signature of mass loss from the AGB stars, which you see. So it is happening. This is the general setup. Instead of moving the star through the grid, you do the usual thing. You put the star at the center, you let the ambient medium flow past, you get a bow shock that's going to heat and transfer momentum to the ejector from the star, plus there'll be some heating that goes into the hot atmosphere of the early type galaxy. It's more complicated than that, as you'll see. So the planetary nebula, I'll just show you this case. It ends its mass loss after about 5,000 years. We pick up the action at 10,000 years, and here's the mass loss. There's been some transfer of momentum, and you get a wake going backward. There's a little bit of fluff that's broken off, but almost all the mass is still here. This goes up to almost about 5 parsecs. Here we go 5 times later, 50,000 years, and here's the ejecta, and you can see that there are instabilities that develop along the surface, but this is the point at which the energy density in the ejecta and the energy density in the shock gas are about the same, so it's going to stop freely expanding and do something else. And now the scale is different. It's 25 kiloparsecs in both directions, and you get to see the bow shock, but there's a re-expansion of that gas that gets shocked. It flows past the ejector. It starts to pull out various tons of material. This is 100,000 years, this is 200,000 years, and you get not only mixing of the gas, you get a lot of shocks going into the gas. So the reheated material mixes in and shocks the ejector from the planetary nebula, and this goes on. This is we have it longer than 400,000 years. You'll notice, though, that there is some wake material that remains cool, and there are 2 reasons for that. One is that the transfer of momentum wasn't that great, but more importantly, radiative losses keep it cool, and you might expect radiative losses to be greater for higher metallicity material. So we hope there would be a bias whereby the higher metallicity material would radiate more rapidly, it would be the material that didn't get joined into the hot ambient medium, and it would do something else, like make stars. And that, when you then add up the amount of gas that flows off the grid that's still cool, has cooled down, it's about 30% of the ejecta, maybe a little more, maybe a little less. There's another stage, the slow mass loss stage, where the wake is a little different, and you still get a fraction of the mass that remains cool. Of course, the higher metallicity material, and there are times when the star is below the velocity dispersion as it goes to the outer part of its orbit. If it loses mass there, it's not going to heat up quite as much. So what happens to the ejecta? Let me just go back one. So any extra heating of the ambient material, this stuff is going to float up. Stuff that's a little cooler than the ambient, that's going to fall down, and they'll come into pressure equilibrium. The really cold stuff has no buoyancy, and it just falls. Okay. So the effect that we found, that there would be a very strong differentiation by metallicity or velocity, wasn't as great as we thought. And of course, it's a time scale problem. And it may be due to the resolution and properties of the simulation. There are some improvements that one can be made. I will not be making those improvements, but I invite anyone who'd like to do a better calculation, and I can tell you some of the things, some of the ways that I think the calculation could be improved. In any case, this simulation would show that there's some fraction of cold gas, or gas lost from planetary nebula, that remains cold and can build up in early type galaxies, and we see it. We see some of it. So that's the first part. Now this part, I was trying to think of a nice way to show that the Conroy et al. Paper was wrong, but it's been stated 2 times at least, and most recently by Phil. So I'm not going to go through all this rather pedantic exercise to show what's going on, but just to say that if you had gas without cooling and without supernovae, that you can show that the temperature of the high atmosphere would go to the stellar velocity dispersion temperature, and the gas density would just slowly build up with time. Eventually, it builds up with time such that the cooling becomes rather important, and that is the classic cooling flow problem. So let's not... so you need something else aside from HEB cooling if you're going to oppose the radiative cooling, and you know what they are: supernovae conduction and AGNs. And supernovae, as I'll show you, works great for lower mass galaxies. So now the temperature of the incoming gas can be represented by that stellar velocity dispersion temperature plus the heating you get from supernovae. And then if you didn't have radiative cooling, that would now approach a new temperature. If that temperature were greater than the escape temperature, then the gas is rendered unbound as a wind. And of course, since this is independent of galaxy, but the escape temperature depends on the depth of the potential well, whether or not you drive a wind depends on the mass of the galaxy. And so for some mass, a particular mass galaxy, there's some radius beyond which it's energetically feasible to drive a wind by supernovae, and within which it's not. And so within some critical radius, the gas cools and would accrete, and beyond that radius, it flows outward. Now for low mass galaxies, this goes right to the center, and you can drive a galactic wind everywhere. And for the more massive galaxies, this goes beyond, say, the effective radius, and then most of the mass loss from the stars is just accumulating in the galaxy. Okay. So I think that's just what I said here. And that leads to the problems that we've been hearing a lot about. And you know the solutions to them. I'm going to offer some other ideas, and I'll warn you, they're probably wrong, but I think at this point, why not bring up some crazy ideas? And the first idea is, do we need to prevent cooling flows? Now, I'll show you it takes one pretty nice visit to a tooth fairy for this one. But, okay, so the cooling rate is, or the mass loss rate from stars, it's kind of interesting that they're the same, is a few tenths of a solar mass a year for a healthy early type galaxy. And for normal IMF, you'd see star formation that was actually rather easy to detect. And let me show you how easy it is to detect this in the nearby galaxies. So this is a paper by Allison Ford and myself of 4 red and dead galaxies, 2 that are in the field, 1 that's a classic cooling flow galaxy in the middle of a group that's falling into the Virgo cluster, presumably, and 1 that's in the Virgo cluster. Okay. And if you do imaging in the UV, where the galaxy is pretty dark, you pick up these things, which, trust me, if you do the various corrections and tests, these are star clusters that you're seeing. And you can see these are either individual stars on the main sequence or star clusters dominated by a few young stars. You get a color magnitude diagram, and these are the more recent stars, and these are the somewhat older star clusters. And then at some point you can't follow them anymore. You can follow the star formation. Sorry that this is a little smaller than I'd like. Actually, I can see it just fine. But, this is star formation rate, 10 to the minus 3 solar masses a year, 10 to the minus 4, 10 to the minus 5, 10 to the minus 6. And if you just follow this line, this is age, 1 gig a year, 2 gig a years. You can actually reconstruct the star formation rate over the last 1.5 or 2 giga years. And for these 4 galaxies, it was pretty level, at a few by 10 to the minus 4 solar masses per year. In some of them, it really has dropped recently, which is bizarre. Those should be the stars that are easiest to find. In any case, the star formation rate is fairly low. In our proposal, we predicted dramatic differences between these 4 galaxies, and there are almost none. So nature is, doing its usual silly thing to us. Okay, so, let me go back to where we were. Okay, so maybe this, if you're going to form stars, you can't form high mass stars. You see them too easily. Maybe you only form low mass stars. Okay. And there is some support for a low mass weighted stellar mass distribution. There was an old calculation that said you can't really change the mass to light ratio, but it seems that the mass to light ratio is different for these galaxies. We do see some H1CO, so there's fuel for this stuff. So there are some virtues to this. I think that was the, yeah, okay. So the stellar mass forms stars. We're going to posit that most of the mass goes into low mass stars. You get a very small amount of high mass star formation. And this should depend how many, the mass of low mass stars you make depends on how large the the wind radius is, right? If you have a massive galaxy where there's very little wind, then you're going to make a heavier IMF than if you have a less massive galaxy where you can just drive the gas out as a supernova wind or galactic wind. And that, in fact, is the case that you see. You see an increasingly heavy IMF as you go to the more massive galaxies. So, in some qualitative sense, this seems to hold together. The only problem is that you're confined to mainly making stars below about 1 or 2 solar masses. Okay. So that's the first bad idea for the day here.
Didn't Bill actually predict this in a paper about 1993 or so, that those cooling flows would make only stars below 2 solar masses?
Well, he discussed what would happen if you made a lot of low-mass stars and how that would change the mass-to-light ratio. And if you put them all in the center, you violate observations. Yeah.
But observations in 1993.
Yeah, and also it's not obvious you make them all right in the center. If you distribute them, it's easier. You certainly saw that the star formation you see is distributed in the galaxy. Okay. So it has a number of other virtues. It just depends on the potential wellness stellar mass loss in the galaxy. And so if you were relying on HEN heating and that were proportional to the mass of the supermassive black hole, you might have differences depending whether or not you have an overweight or underweight supermassive black hole. But in this case, you don't have to worry about that sort of thing. So this is one possibility, that it's not really quenching, it's just low mass star formation. Okay. Here's another thing, warming flows. Words I've only said one other time. Oops, that was I gave a talk on this in 1990 in Cambridge. I think I did mainly just to jerk Andy Fabian's chain. And it worked. I gotta say, it's really quite a violent reaction. But he didn't hit me, although he didn't talk to me for 2 years. Okay, so this is the way warming flows work, the opposite of cooling flows. But it's conceptually it's feasible. It's just when you do the calculations, it never quite seems to work. But bear with me. Okay, so you have this applies. We're going to look at this in a system with sufficient conductive heating, although in some sense you actually just need a sort of heating that goes on. And so if we look at the centrals in groups, richer groups and clusters of galaxies where conduction can be important, what you see when you look at the X-ray temperature distribution is this is dropped by about a factor of 2 or maybe a little more into the center. Okay. You see that, and the cooling radius within which you have to worry about things cooling, typically 50 to 100 kiloparsecs. So there is the central galaxy, and there's stellar mass loss. It thermalizes itself to about a kilovolt in these galaxies. And this provides essentially an inner boundary condition on the temperature. And then you have heating coming in. Let's say that it is conductive heating, and that's going to heat the gas. The gas is going to flow out very slowly as it becomes heated, and so you're going to have an outflow for the hot gas. The cold gas that didn't make it is still there and forms the few stars. It has some virtues conceptually. It might reproduce the temperature gradient, and it prevents it saves your cooling flow catastrophe. So that's all good. The problems are that it's not quite obvious this leads to the desired solution. As far as I know, almost everyone who has worked on conduction doesn't get the the solution that they hoped they would get when they started the calculation. And Mike Anderson and I tried this particular one, didn't really get a solution to the 1D equations that we liked in this case. But maybe more sophisticated treatments will show it works out. There are a few other little problems for M80. For some galaxies, you would have expected a central temperature of about 1 keV, and you see 2 keV. It comes out about right for M87, it turns out. It's not going to work too well for isolated ellipticals, we think, unless the temperature increases as you go out. Okay, so this is the end of the second bad idea for this talk, and I think I'll end there.
Question?
I had a question about the low mass star formation. Do we see any evidence for that happening in the Milky Way where it's easier potentially to observe?
Sure, the Taurus molecular cloud, it's almost all low mass star formation. You don't see the high mass stars. So there are examples of that, but maybe it just hasn't gotten around to making the high mass stars. Is there someone who actually knows about star formation who can answer that more authoritatively?
Yes, it's very authoritative.
Taurus was completely, has the same exact IMF as every other star formation region in the galaxy, even though it doesn't form the high mass star. It's exactly the same, almost exactly the same.
It's okay, as long as you don't form the high mass stars, you'll just never see the star formation. So, you know, what's different about these systems? Well, the pressures are very high. The pressure is NT is 10 to the 6.
Metallicity is very high too. Metallicity is very high too, which leads to
Yeah.
greater fragmentation.
Right. Metallicity is high, the pressure is high. And, you know, it's just really hard to see this stuff.
Question of it?
So one way you could perhaps go about looking at this is if you look at star formation indicators in the mid-infrared, because this is dust heated not only by the UV light but also by the optical starlight. So if you saw very different star formation rates in the mid-infrared to what you saw in the UV, for instance, or the H-alpha line, and I don't think we see that in the galaxies, but of course
There is
more to be done
some,
in that area.
there is some weird dust. I mean, so there is some extra heat. It's just you can't convince yourself it's not the way over dominant full starlight.
Yeah, that's the problem. I mean, that's will be on site.
It's just nasty.
So you do see the silicon or silicate feature at 10 microns, because I did that and tried to use it as an age indicator. But I never thought about, you know, what fraction of that could be due to star formation and which was stellar mass loss.
Further questions, and move on to the next talk.